All right. Appreciate everyone coming here and not attending the Phoenix Open today. And this is the last talk of this track too. And with that being said, we'll just get started. Imagine deploying an app within few seconds today, right? There are no servers, nothing to manage, no infrastructure headaches, and just pure code in motion. How beautiful that is. That's the magic of serverless computing, and it almost feels effortless when we think about it, because beneath that smooth performance lies a quiet misconception that serverless somehow means less responsibility. So, in reality, the faster we move, the easier it becomes for us to overlook those hidden risks. And because serverless architectures are event driven, they are highly dynamic, and they define and enforce trust boundaries, kind of these things become paramount. Now, traditional security models built for lasting infrastructures falter amid these ephemeral executions, right? And the core of the serverless architecture is a Lambda function, is something which is more ephemeral, and fine-grained service integrations that together expand the attack surface. So, with this in mind today, Nimish and I will help you navigate security in the serverless world as the risks still bite, even though there are no servers in sight. And before we dive in, let's take a quick look at how the infra abstraction has evolved over the last 5 decades. All right, so before we get started, just a quick disclaimer that I am not representing my employer today. And before we also begin, I just wanted to just understand the audience in terms of how many of us are aware of cloud computing or they are running workloads on cloud. Oh, wow. Okay. Thank you. That's quite a lot of you, actually. So I guess all of us can relate to this evolution in some aspect or the other. The computing infrastructure has definitely undergone a massive transformation from the physical racks in data centers to invisible functions in the cloud. And this story actually begins with the bare metal era, which I also refer as the bullock cart era, right? Where physical servers running one operating system and one workload. Now, in the beginning, you owned the entire cart, which means one cart, one rider, and one destination, right? So you fed the bull, you kind of fixed the wheels, and you cleaned the mess. And also, you pushed when it got stuck. And if the cart broke, then what would you do? You weren't going anywhere that day. And that's what we saw in the last session as well, where he mentioned what happens if an incident is logged in at 4:50 p.m. on a Friday, right? Now that's bare metal for you. It's powerful. It is also predictable, but painfully slow to scale. And guess what? Some critical routes still use bullock carts today because they never fail. So which means that we still rely on the bare metal even today. A lot of industries, right, talk about healthcare, fintech. A lot of these industries still rely on prem servers. And then came virtualization, a revolution that let one physical server host multiple virtual machines. We also call it the bus and the carpool era. Same road, same engine, multiple passengers with different destinations. Better efficiency and faster recovery if one rider dropped off and fewer empty seats, right? But now you needed schedules, tickets, and rules, or otherwise chaos would follow, right? So welcome to the early cloud where infra became elastic, more scalable, and it unlocked better resource usage, faster recovery, and flexibility. So tools like VMware, Hyper-V, which is hypervisor, and later AWS EC2 changed how we thought about compute in general. Now, as applications grew, teams wanted lightweight, portable environment, and that's where containers arrived. With Docker, Kubernetes, developers could now package tools and basically have their code and dependencies all kind of bundled together and deploy anywhere and scale faster. Now, this was the era of DevOps, automation, and microservices, bringing more agility and also new orchestration complexities. And finally, in 2014, AWS launched Lambda, making or marking the start of serverless era, which is also called as the teleportation era. Because you don't book a ride, you don't see a car, you just appear at your destination. You upload the code, you trigger an event, and voila, you're done. Now, it accelerated innovation, but also blurred the responsibility because developers lost visibility into what was once under their control. And that is something what we'll talk about in detail today in today's session. So before we go any further, I think this is something which you want to understand, which is the shared responsibility model on the cloud in general. Now, here we have two personas. One is the cloud customer, and the other is the cloud provider. The shared responsibility model defines what cloud provider secures versus what we as users still own. But in serverless, this model changes shape, right? And sometimes it's easy to forget where our line ends. In traditional models like EC2, the split is clear. The provider secures the infrastructure, hardware, networking, hypervisor, but we manage the OS, runtime, applications, or even data for that matter. So there's full control, but also full responsibility for patching, configuration, and monitoring. Whereas in serverless, the cloud provider handles almost everything below the function layer, which is servers, runtime, scaling, and patching. So what do we do then, right? Because this doesn't mean there is no responsibility on us. We still own identities and access management, also known as IAM, data security and encryption, code quality and dependencies, configurations and triggers. So the shift to serverless moves our attention up the stack from infra to logic and event flows. And the key is to apply the DevSecOps principles like validating the inputs, restrict the IAM roles, audit the configurations periodically, and monitor the function behavior. So with that being said, we move on to now analyze more on the serverless attack surface. The first one up here is the trigger and event source risks. So event sources are your front door, right? Because attackers can inject malicious payloads via APIs, object metadata, or messages in general. So when we think event driven, we talk about API gateways, we talk about SQS, SNS, all these different terminologies you might be aware of. Now, because event flows are trusted, a bad event can trigger a chain of functions, right? And what is the quick defense here? Validate schemas at the edge and enforce event signing or origin checks, which means we need to understand what kind of event is flowing into our pipelines. Is that the right event or not? Then the second one up here is the functional level vulnerabilities. So individual functions often carry the risk from outdated packages to unsafe deserializations, right? A single vulnerable library like any NPM module or a Python dependency can lead to code execution or secrets leakage. So what is the quick defense here? Is implement dependency scanning, runtime protection, and avoid those secrets, or maybe just store them in a sensitive place and not hardcode that as plain environment variables in your Lambda functions. And next up is the platform misconfigurations. Now, what does this refer to? So the underlying infrastructure, what we spin up today, a lot of automated tools are available like Terraform, CloudFormation. These help us automate the entire pipeline of spinning up resources. So please ensure the wildcard permissions are in check. Then the public buckets are not kept public anymore because that let the attackers pivot widely. So misconfigurations scale the blast radius, as we already spoke about that before. So what's the quick defense here? Enforce least privilege, automate the config scans, and posture checks. Now, CI/CD risks I would classify as a subcategory to the platform misconfiguration, but it is essential for all of us to understand what kind of risk do these CI/CD pipelines today carry, because these pipelines are also an attack vector. So if CI/CD is compromised, attackers can ship malicious builds or insecure configurations at scale. So what's the quick defense here? Require artifact signing again, have immutable builds, and security gates in your pipelines. Simple, isn't it? And finally, monitoring gaps. Again, this is something which I piggyback on top of the platform misconfigurations, because serverless can be noisy, but it also is blind. So if I don't capture the right telemetry, I won't be able to get the insights from the logs. Incidents are hard to detect and investigate further. So what's the quick defense here? Enable distributed tracing. For example, in AWS, you have something called as X-ray that really helps trace the logs better through the pipeline. Then have a centralized logging or a queryable kind of interface, and have some retention policies tuned for investigations. You can't have the log only for a day or only for a few hours. So make sure you have the right retention policies in check. And with that, I would like to hand it over to Nimish for the next slide.
Thanks, Shivam. Moving on, we with this slide we try to perform a fundamental or a basic threat mapping to the conventional security frameworks. Obviously, our topic around serverless architecture is a specific one, and we don't have a particular security framework, allocated to it. So, a basic tenet of this session is that serverless doesn't move responsibility; it relocates it. So, and after speaking with different GRC analysts working with the serverless and the function-based services and applications, we found that in addition to security engineering constraints associated with the infrastructure abstraction within the serverless architecture, risk assessments and building accurate RACI matrices is another major challenge from a governance perspective. So this table maps three high-impact serverless risks to two popular frameworks: the Open Web Application Security Project Top 10 and the Common Web Enumerations or the CWE Top 25, and pairs each with concise mitigation steps that you can ship come Monday morning. I'll be taking AWS as standard cloud provider just for the sake of reference, but they're obviously replicable to other CSPs as well. Uh, so first is platform misconfiguration, or within OWASP, it's security logging, monitoring failures, CWE, insufficient logging. Now in serverless, the platform is your runtime. Misconfigurations, especially missing or weak logging, turn incidents into silent failures. As if you can't see it, you can't defend it. For mitigation strategy, the first one would be and the most essential one, in fact, would be to capture the right logs by default. And you can do that by enabling CloudTrail and Cloud Lake, Lambda and API gateway logs, S3 data events, and VPC flow logs for egress paths. Now, enabling logs is just the first, albeit an important step, but we also need to make logs usable. So for that, we need to structure them, say based on the principal role, request ID, resource ARN, and consolidate and centralize them into any SIEM solution. AWS has a security hub as a native SIEM solution. Azure has Sentinel. We can use any of them, and then Wazoo. They are like open source ones. And we can configure detection rules for anomaly detection. Now, the second one is runtime monitoring. This can be achieved by configuring, say, CloudWatch metrics and alerts for error ratios, throttle spikes, cold start anomalies, wire alarms to on-call engineers, and auto remediation runbooks. As a reminder, logging isn't just a nice to have, it is the control surface for forensics, containment, and documenting audit trails. Second is event injection, or just injection in OWASP and improper control of code within the CWE. Now, serverless apps are event fabrics that are sort of knitted together using a plethora of API requests, S3 object puts, SQS messages, schedulers, and many other aspects as well, wherein each event is an ingress point. An event injection captures risk of unvalidated input, forcing unintended behavior, code paths, or even straight up denial of service. Now, mitigation strategy primarily revolves around configuring boundaries to enforce at the edge, which includes schema and content validation at the API gateway security that rejects any malformed JSON or any oversized payloads. It also includes strong identity on events using JWT authorizers or configuring MTLS if feasible. And third could be configuring a fail safety that can be done by using DL queues, dead letter queues, and or ASIC triggers, essentially item potency keys to prevent replay attacks. The core objective is that if an attacker injects into the stream, these boundaries stop lateral movement and keep the blast radius confined and small. And the last one is vulnerable dependencies. The similar name, use of unmaintained third-party components is also an additional control within the CWE. Now, in serverless, dependencies are the supply chain embedded within the Lambda layers or container images and transitive packages. So for practical hardening or mitigation strategy, you can utilize steps like producing an SBOM with tools like Maven and verifying signatures for images and layers and blocking any unsigned artifacts in the CI pipeline. Next, to scan early and scan always is another crucial strategy for runtime protection. Software component analysis, or the SCA scans, to analyze open source components, and static as well as dynamic application security testing for analyzing code functions before and after execution, and image scans on pull requests. Third can be constrain egress and third-party access, which includes different steps like VPC integration with egress controls, private package repos, and scoped OAuth or API tokens, and secret rotations as part of privileged access management. The result will be fewer moving parts, fewer surprises, and less attacker leverage through your build chain. Now, this section often gets the management's attention. And for any CIOs or CTOs or CISOs, this is the money aspect. We've established that serverless isn't a silver bullet and the responsibility shifts. But what's the tangible cost when that responsibility isn't met? If you look at this chart, it illustrates the rapid, almost exponential growth of the serverless computing market. The compound annual growth is around 25%, which shows that it's just isn't a trend. It's a fundamental paradigm shift, as Shivam mentioned, from the VMs era to containers and now event-driven workloads. A huge portion of this is driven by function as a service, or FaaS. So we use serverless and FaaS interchangeably as well. And it's no wonder that it's a fan favorite among many startups and MSMEs, precisely because of these cost savings. Now, that growth, however, also magnifies risk. The second graph, which projects the losses due to serverless related breaches. And this, we have mapped it with across different major incidents that had serverless workloads somewhere within the pipeline. It wasn't really like directly or solely part of that, but one aspect of it. And obviously, as the serverless market grows, so will the losses by associated security incidents, which is what we have modeled into by taking three scenarios essentially in the second chart: base, high, and high plus. Essentially, we tune up across each level, and based on that, in the base one, we can see that the projected losses are going from tens of millions to hundreds of millions by the year 2030. And then another neat aspect of that is the cyber insurance. The third chart shows the global cyber insurance market projection in billions USD. And this is based on Gallagher's 2026 Cyber Insurance Market Outlook Coverage Report. The headline is that the market is estimated around 16 billion, 20 billion till as of last year, and the forecast is that it's going to double by 2030. Now, that growth is not just more companies buying policies, it also reflects the strict adherence by the underwriting departments reacting to losses and experiencing uncertainties in the modern environments, especially modern ephemeral environments. And cyber premiums rose sharply when ransomware and major events drove major losses. And even when uh, pricing cools down, the carriers keep tightening what they require to write or renew the policies. That being said, we will shift the session over to you and ask you about what other gaps and vulnerabilities do you think are associated with the serverless architecture and function-based environments. So if you can please scan the QR code, it will let you, add, text to your as a reply, and it will present it over there.
No phishing, guys. It's a genuine QR code. Yeah.
We'll give it a couple of minutes for the replies to trickle in. Anything from your own experience that you may have seen?
Could be cloud specific or agnostic, anything what comes to your mind or you have experience with in general. Right. Amazing. Absolutely. I think logging is something every organization spends a lot on in general because that's where the threat hunting also starts from, right?
That also ties into the alert fatigue in general, because there's so many false positives. Financial exhaustion, that exception. But yeah, that is specifically with the compliance and legal departments. At least I've seen that happening quite often. That's true. Yeah, overpermissive IAM roles is definitely the number one. Attack service, third-party attack chains is another one. With the vulnerable dependencies and the function-based workloads having numerous sources from different open source platforms, it is definitely difficult to keep a track of it, especially for some of you who are from the vulnerability management portfolio. The patch management is a nightmare for the serverless workload.
Somebody put in complex attack surfaces. Do you guys want to
Yeah.
talk more about that? Are you guys talking in terms of serverless environment in general? That's all right.
You can take it. Question then? Moving on. In this section, we are shifting to a more practical insights via a case study, which we have developed and open sourced and we call it Links Lab. Now, as part of our research, we needed a repeatable home lab environment. The Links Lab automates it. It stands up essentially an AWS stack. Well, we used AWS, but the core objective or the future objective is to make it CSP agnostic. The AWS stack that implements machine learning or any AI workload for our case study, we have taken simple sentiment analysis workload. That gives us a consistent target to validate controls, test security hypotheses, and generate evidence without sort of hand building infrastructure every time. So to provide a context, the point of Links Lab is simple. It's a command line interface driven cloud lab utility that can provision an AWS serverless stack. Let us exercise realistic attack and defense scenarios and then tear it down cleanly when we are done. The workload itself is intentionally simple. As I mentioned, it's about the sentiment analysis workload. There are numerous models, pre-trained models to choose from in the Amazon Bedrock. Sentiment analysis is not only simple, but it also has numerous use cases specifically for those customer support AI chatbots. Where we type the first thing as connect to live agent. Um, so yeah, that keeps the focus on security controls and failure modes and not application complexity in general. Now, starting from the left, the user hits an API gateway. This is the public interface where a client passes in a request, typically a JSON work payload with the text and an instruction for the model. And obviously, it can also consist of XML or some of those SOAP API calls and queries for GraphQL. And then behind the API, we have two Lambda functions, an authorizer Lambda and a worker Lambda. The authorizer is for access control, and the worker is for actual processing. I will walk through the path using the arrows on the slide. The first key point, the stack is a real AWS deployment and not a mock. The authorizer Lambda is invoked by an API gateway as part of the request flow. And this is where we enforce whether the request is allowed to proceed or not. Then we have the supporting components you would expect in a production like serverless workflow. There's the secrets manager for storing sensitive configuration or tokens. And there is an S3 bucket that records requests and responses for traceability and log monitoring. The actual sentiment generation is done via a Bedrock hosted model, which is configurable depending on what your AWS account has access to. Now, the authorizer Lambda integrates with the secrets manager. And the reason is straightforward. You do not want secrets or tokens hard-coded in code or configuration. So the authorizer fetches what it needs securely, validates the caller, validates the context, and then based on that takes the decision of either allowing or blocking the request. Now, separately, we also have an S3 bucket in the stack. This is used for logging or recording requests and response artifacts. Now, from a security testing standpoint, that is important because it gives you an evidence trail for what was sent in and what came back. On the right is the model component, Amazon Bedrock. Now, we show for the sentiment analysis model, we have taken the Llama 3 model, which is the one with 8 billion tokens as an example model. But again, like I said, there's numerous choices within the platform. So the worker Lambda to Bedrock. Now that is the one that calls the Bedrock. The flow is essentially the API gateway receives the request, the authorizer approves it, and the worker invokes the model with the input text and task instructions. Now the output we expect is a sentiment label, which could be positive, negative, or neutral. The response comes back through the worker Lambda, then back through the API gateway to the user. Now, two things to remember on this slide. One thing is a reproducible lab stack that actually deploys into the AWS account. And second, the intent of the workflow is the sentiment analysis on text, and the security value is that we can now test controls within each boundary. Yeah. So for the next slide, we actually have a demo for the same. I hope it's visible to everyone in the back. Sorry. The key point is that we treat infrastructure as disposable. So this is essentially creating that stack. We create the stack, validate it end to end, and then destroy it. That makes it safer to iterate and easier to run the same experiment multiple times. Now in the terminal, you see the lab being created. The repo's workflow is install the Python dependencies, set the AWS CLI credentials and region, set an environment variable used for API authorization, and then run the driver with a create action to provision the stack. So now while the create is running, the tool is effectively orchestrating the build out of AWS resources we just discussed. From a security engineering standpoint, that this is useful because it gives us repeatability. We can test the same IAM policies, the same authorization path, the same logging behavior, and compare outcomes across different scenarios. Now, as the stack comes up, we pivot to the AWS console to verify that the resources are being created as expected. Practically, this is where you confirm that the API gateway exists, the authorizer Lambda exists with the right permissions, it's attached to the API root, the worker Lambda exists with the right and the correct permissions, and that the supporting resources like the S3 bucket and secrets manager are also present. Now, let me be explicit about why the authorizer Lambda exists. As I mentioned in the previous slide, it is to implement essentially the request level authorization. In the Links Labs baseline flow, the API is invoked with a bearer token header. The authorizer Lambda validates that the caller is allowed to invoke the endpoint and blocks requests that do not meet the policy. Now, only after authorization succeeds will the worker Lambda execute. The worker reads request parameters, calls the bedrock model, and then returns the model output to the API response. Now, importantly, for investigation and reproducibility, the request and response are also written to the S3 bucket so we can inspect inputs, outputs, and patterns across the runs. Now, once the stack is ready, Links Lab then outputs the API gateway invocation URL via a get URL action. This is the endpoint you can use from a client like Postman. And in the repo, this is a distinct step so that you do not have to hunt through the console for the deployed stage URL. Now in Postman, the demo uses two main inputs. The first is input text, as you saw, which is the raw text. And the second is input task, which tells the model what operation you want. And in this case, it is a sentiment analysis model. Now the separation is important because it mirrors the common prompt plus instruction pattern and helps us reason about where validation and policy should be enforced. And when we hit send, the request API, as you saw, goes to the API gateway, authorizer Lambda validates the token, and if allowed, the worker Lambda invokes the model. For the logging, S3 bucket is where the workflow logs and requests or records the requests and responses. For security testing, it is valuable, obviously, because it supports forensics and forensics-based incident response and experiment reproducibility. And we can also compare exactly what went in, what the model returned, and how your defensive strategies change according to the behavior of the workload. And then from there, we um, move on to everything is complete, we can then move on to destroying the stack and then repeating the whole process again. I guess the video is done. And now we'll move to the adversarial path, wherein I think Shivam will talk about the attack and defense scenarios within the context of Links Lab.
All right. Thank you. Well, that was quite something, right? All of us are tired, but the good part is all these services are available for free on AWS, and that's the reason why we picked or chose those services for building up Linux Links Lab. Now, what we'll do is we will run through some attack and defense scenarios here. And these will be something we have already covered in some parts of the presentation. So it will be easier for us to understand what the attack vector is, what the defense is, and we'll just breeze through these slides, right? So the first one is, as we saw, the user is able to call the API. Now, in this example, we saw that there was a text being sent out in the API call, and there was an operation which we also passed in through the API. Now, imagine there is no kind of sanity checks happening on that request, right? That's where the injection attacks happen. And that's one of the things which we have mentioned there on the slide, that that's the possibility where the malicious inputs can be injected. So moving on to the second example, which is a platform misconfiguration. Now, when we talk about spinning up a resource, there are different things which come into play. There are IAM policies, there are roles which need to be configured. Now, as part of that entire process, if let's say we miss configuring a variable, which allows us to log records from coming into the Lambda function, right? There's the deny effect policy, which you can change, and because of which you can disable logging for that Lambda function. So if that happens, that's where we are calling it as the point of failed forensics. And in order to not allow those situations to happen, we need to ensure that there are proper guardrails in place, which ensure that these misconfigurations or configuration security drifts are being tracked, and none of the users are able to kind of deploy such services in production workloads. And lastly, we spoke about the functional level vulnerabilities. And here, what we are talking about is a particular vulnerability in a third party package, right? Which we can cause these secrets to be leaked out. And that's what one of the things which we want to ensure as well, that how do we make this entire flow more secure? And that's where the dependency pinning, if you know the exact version, which version is in divest mode, we shouldn't be using those versions, and try to use the latest versions with the relevant security upgrades. And SBOM also comes handy in those scenarios. Now, with that being said, we move on to the last section of today's presentation, which is the final takeaways and best practices. And Nimish, you want to?
So the first one, serverless removes the servers, not the need to understand what is actually happening. If you cannot trace the full request path and permission boundaries, you end up doing mental gymnastics during the incident triaging instead of having clear controls and visibility upfront.
Right. So you still own the identity, data, dependencies, and conflicts. And that's the third time I'm telling that in this presentation.
Thank you. Well, with the abstraction and hyperscalable function triggers, shipping gets easy. So you want to move faster to prod to feel good, and also to get rid of the PM, writing your back for lingering Scrum blocker. But if you're not gating deployments with automated security checks and least privilege reviews, you end up throwing up during this game. As some of you who watched the office know what happened with my case.
Right. So enhance your production pipelines via structured velocity. I think that's the term we all want to kind of understand a little better.
Isolation is a design choice and not just a vibe.
Right. Well said. Because security is the blast radius management. We need to isolate by function, by the account, by the VPC, and by the tenant. All right.
Function-driven and highly abstracted workloads can feel like the compound V for production, faster shipping, auto scaling, and fewer servers to babysit. But the same trust me bro abstraction can catch you off guard during incident response if you do not enforce trust boundaries, validate inputs, and isolate event commit.
Absolutely. So you need to validate the schemas at the edge and keep handlers small and idempotent.
So this is what a serverless heavy architecture feels like. without comprehensive telemetry. Everything looks fine until it is not.
So you need traces that follow an event across the services and logs which can be queried.
Lastly, serverless changes the, you lose the server, not the responsibility. It changes the shape of risk, and your job is to design for the failure.
And that's all we had for today. Thank you.